All right, this is 7-3, Triangle Similarity. So a shape is similar to another shape if all of its corresponding angles are the same. That just means that two triangles are similar if they're the same triangle but a different size. That's probably the most useful piece of information there, is that if we're wondering if two triangles are similar, we just have to check if they're the same triangle, just scaled up or down by a certain amount. And there's a couple different ways that we can know something is two triangles are similar. And these are listed below here. First we have angle. Obviously, if two of the two consecutive angles are the same in the triangle, that means all three of them are the same as well. You know, if you know two angles, you know the third angle also, because all of them add to 180. So if two consecutive angles are the same, the triangles are similar. Then we have side. If all three sides correspond to each other proportionally, and that's important. They don't have to be the same value, but they have to be scaled up by the same amount. Then they're similar. And then we have side angle side. If two sides correspond and the angle between them is the same, they are similar. So again, with the side lengths, it doesn't need to be the exact same. It just needs to be scaled up by the same amount. The angles actually do have to be the same value, though. So we are going to look at these triangles here and decide if they're similar or not. So this first pair of triangles, we have an angle that's 29 and an angle that's 89 and an angle that's 62. We don't technically know if two of these angles are the same unless we figure out what the third angle is. And it turns out if you subtract 89 and 62 from 180, you get 29. And because then we have two consecutive angles that are identical in these two triangles, even though they're different sizes, it means that they are similar, yes, using the angle idea that we have up above. So angle, they are similar, yes. Number 2, we have two different triangles here. We have an angle, and I'm going to highlight these really quickly. We have an angle, and then we have a side, just like that. So 5 and 10, 5 is half of 10, so that would be fine, but we don't have another side. That's the first issue that we have here, and we also have different angles. That yellow angle is not supposed to change. We divided it in half, but that made a completely different triangle. The other two angles have to be much bigger because we divided this first angle by 2, so it makes a completely different triangle. So the angles need to be exactly the same, but the side lengths, those are the ones that could be proportionate. So this is a no, it is not, they're not similar. So we don't need a reason, they're just not, right? Also notice that they don't look like the same triangle, right? One of these looks like kind of like an isosceles, skinny, tall isosceles triangle, and this one looks almost like a right triangle. Totally different. Okay, so number 3, we have a side, or an angle that's 42 and 42, and then we have two side lengths, a 6 and a 4, and then we have an angle that's 90 degrees right there. So even if we completely ignore the side length, we have two consecutive equal angles, right? We have 42 and 90 and 42 and 90, and therefore we know that this last angle in both of these triangles has to be the same, and so this one is going to be a yes, they are similar, using angle. That's going to be my abbreviation for angle. Number 4, we have one triangle that's 1, 1, 1. This, if you'll remember, is a equilateral triangle because it has all of the same sides. And equilateral triangles have all same angles in here. So all of those angles inside of that triangle have to be 60 degrees because we've already decided that equilateral triangles have 60-degree angles. And so there's already an issue, right? Because it looks very similar. These look like the same triangle, but only one of these angles is 60. The other one is close to 60, but not, right? This one is not 60, and so this is a no. They're not similar, because they don't have all their angles the same. Number 5 here, we have two triangles that are sort of set inside of each other. Both of them share this 90-degree angle in the corner. And because, notice that these two like hypotenuses of the triangles are parallel, that means that when they intersect the same line, like here and here, they're going to make the same angle because they're essentially the same line but scooted over, right? Same thing for up here. These angles, we don't know what they are, but we know that they're the same. So that means we have 3 actually of the same angles, which is exactly what we need to say that this is a yes, for sure similar by angle. This last one, we have 2 triangles that are also touching each other. So, and we have one indicating that it's the same. So we have 6 right here and 6 here. So if I were to draw these separately, going somewhere else. If I were to draw them separately, I would have like a small triangle with 3, 6, and 6, and a big triangle with 6, 12, and 12. So our job, we don't have any angles on this one, our job is to decide if these are proportionate. So if we're sizing them up by the same amount. So remember that is multiplying or dividing, right, by something. So we need to decide what are we multiplying by to get from 3 to 6. And that's times 2, right? 3 times 2 makes 6. So is 6 to 12 and 6 to 12. Those are both times 2. So as long as all of those match, then those 2 triangles are similar because we sized the whole triangle up by 2, which makes similar triangles. So this is also a yes, and this is by side, side, side. Because all the 3 sides are scaled up proportionally, and so we can tell that it is similar. So it says, how do you decide whether or not number 6 was similar without angles? We decided because corresponding sides were scaled up proportionally. It's an important word. Proportionally. Perfect. Okay. Let's look at the back here. So, when we talk about side lengths of a triangle, if we know 2 triangles are similar, it gives us the ability to find missing side lengths. So similar triangles have proportional, that's what we just decided, proportional side lengths, meaning that each side grows or shrinks by the same portion. We can use similarity to find missing side lengths in similar triangles by determining what value each side is being multiplied by. There we go. Be careful to match up corresponding sides from each triangle correctly. So we just have to make sure that we know which sides correspond to each other, and we have to figure out how they're being scaled, and then that's how we can find the missing sides. And so a lot of this is finding what value it's scaled up by. So this here is just indicating that all of the proportions are the same. So the bigger triangle has been scaled up by P. Here's my P on both sides, so that the same sides, A and A, are going to be equal, but one of them is going to be scaled up. So one of them is like A times P, and the other one's just A. And so these are all just indicating that the same corresponding pairs of sides, right, make equal proportions. The best way to, and I'm going to get one more color, there we go. Well, let's just try a problem here, and we'll talk about what the best ways to do things are here. So it just says assume the triangles in each problem are similar. So we already are just going to assume they're similar and find the missing sides or angles. So we have the smaller triangle here that's 20 and then 11 and 11. And because that one's all filled out, that's going to be a useful triangle for us. So we know that 20 and 31 are corresponding sides. We can tell that those are the same sides of this triangle. We just need to decide how this has been scaled. And you do that by division. So you divide 31 by 20 to figure out what that p value is, like how has it been scaled. 31 divided by 20, grab a calculator. (31 divided by 20 is something, but I can't type properly. There we go. 1.55, which means that we are scaling this up by 1.55, and we just need to match that scalar for the other two. So when we have 11 and something here, we just need to multiply by that same value by 1.55 to get what b needs to be. So 11 times 1.55 is going to be 17.05 or 17.1, depends what you feel like. So that's b. And then one more, we have actually it's the same number, so we know that this also is going to be the same, because a is also going to be 11 times 1.55. 1.55, so also 17.05. So both of those values will be actually the same. Lovely. Okay, so our idea here is that we find the scalar. We find how much bigger one is than the other, and then we use that to scale all the sides correctly. So number 2, we have a filled out triangle here, 18, 16, 21, and a not filled out triangle. So we have to find the corresponding sides, which we can tell visually these two are corresponding. And we just decide, how do we get from here to here? So 21 divided by 16 is 1.3125. Okay, so it's kind of a big decimal, but we do have to preserve all of those numbers. And notice that this time we're going from the bigger triangle to the smaller triangle. So we, when we try to find out what A and B are, we need to be dividing by that number. So it's very important that we know whether or not we're going from the smaller to the bigger or the bigger to the smaller, because once you find that proportion, this 1.3125, that is the number going from the smaller to the bigger, right? Assuming that you divided the bigger number by the smaller number. So we just need to make sure that, like, if we're going from the smaller to the bigger, we're multiplying, and if we're going from the bigger to the smaller, we're dividing. You can tell if you have the right answer if your answer is smaller than what you started with, right? So like if I multiply 18 by 1.3125, I'm gonna get a bigger number, and I don't want a bigger number, I want a smaller number for this triangle. So just double check your work that way. So A is going to be, keep getting scooted there. A is going to be 18 divided by 1.3125, which is, and I will get that, 18 divided by 1.3125. I got 13.71 for that one, and I'm rounding. And B is going to be 16 divided by that same value, So notice that 13.7 is much less than 18, which is the correct, that's right? I want them to be smaller. So I'm just double checking my work there and making sure that it makes sense. 16 divided by 1.3125 is 12.19. And those are our two values. Good. So number 3, this one looks like all mashed up. And that's just because we have two triangles like inside of one another. And what we're going to do actually is I'm just going to redraw the triangles so that they're separate from one another. Here's one of them, and another one is going to be just smaller. So the blue triangle, the one that's highlighted blue, is going to be this one. So I know that this is the 90 degrees, so I kind of rotated it a little bit. 10 is on the bottom, 15 is on the hypotenuse, 12 is on the side. And the other triangle is not going to be the big triangle. It's actually going to be this triangle here. It's going to be that triangle. Ooh, I thought it was a square. So that triangle has a 90-degree angle right there, which means that one of these sides is 12. That's 12 and K and N there. Yeah, okay. So, we have those two different triangles, and we use the same process here to figure out what the number is that we're dividing by. So 12 divided by 10 is 1.2. So that is our scalar amount, and we're dividing by that, actually multiplying, right? Because these ones were going from the smaller to the bigger. So multiplying by that value, so N is going to equal 15 times 1.2 is 18. That's good. And then K is going to be 12 times 1.2. 12 times 1.2, which is 14.4. Okay. Fantastic. So we have N and K, and we made sure to multiply because it's going from the smaller triangle to the bigger triangle. And our answers make sense, so we're gonna go with those. Number 4, we have two similar triangles, and actually what we're solving for in this one is the missing angles, not the missing sides. So we know that the angles in similar triangles are always the same. So alpha, let me try to draw an alpha, there we go. Alpha is going to be 33 because I can tell from the other triangle that this angle should be the same as that, right? And then our other question mark is this y. So if we have 60 here and 33, we take those two things away from 180. And I got 87 for y. So we're just using our skills to figure out what that missing angle is, because we have 2 out of the 3 angles between the two triangles. So those are our missing values. Number 5, we're back to similar triangles, and we're just looking for this b value. So this one gets a little funky because we have 2 sides that are not corresponding, that are the same value. This is indicating that those two things are the same. This and this, right? So what I'm going to do is I'm going to label that x because I know that they're the same, I just don't know what it is, right? And there's actually no corresponding angles here, or I mean side lengths, because B corresponds to 16, 19 corresponds to X, and X corresponds to 32. So we're not actually sure what the scale factor is here. What we do know is that that 19 relates to X and X relates to 32. So what I'm going to do is I'm actually going to set up my problem a little bit like this, where I'm going to set up a proportion. So I know that X relates to 19. I'm using this value and this value. So this over that. Then I'm going to say this is going to have to equal 32 over X. 32 over X. You just have to make sure that you put the right triangle, and I'm not meaning I mean the correct triangle, right? The same triangle on the top and on the bottom. So this is like the larger triangle. And the big triangle is always on the top of the fractions, and then the small triangle is always on the bottom. Anyway, so we set up that proportion, and using our skills of solving with like cross multiply, we can multiply across here and across there. That gives us x squared, because x times x makes x squared, equals 609. That's 19 times 32 is 609. And then we can square root both sides to find out what x is, which is 24.66 approximately, which is helpful because once we have the x value, we can then figure out what the scale factor is here. So now we know that this is 24.66. So now we can divide 24.66 by 19 to figure out what the scale factor is. So now I'm just doing what we were doing before, where we have that value and this value, and we're trying to figure out how we got from one to the other. So 24.66 divided by 19 makes 1.29. I'm going to say 8. I'm rounding a little bit there. So that's our scale factor. And now we can just divide this 16 by 1.298 to figure out what this missing B value is. So from 16 to B, I'm dividing because that's from the bigger triangle to the smaller triangle. So 16, I'm going to say B equals 16 divided by 1.298. 16 divided by 1.298, and that's 12.33 approximately. So that's B. That's fantastic. So that one is a little bit more complicated. We had to set up a proportion there, and that only happens when you don't have any sides that are corresponding that you know what the value is. Because otherwise, normally you can just find the scale factor, but that one was different because we didn't have two sides that corresponded. So one more here. We have two triangles that are similar, but they're back to back. And we're wondering what this angle is here. So notice on the other triangle we have a matching angle here and here, and a matching angle here and here. And so this angle should also be matching that angle. So not too bad. V is just 45. And that's all we're looking for. We're not looking for side lengths. So yeah.